Thanks for the introduction, and hello everyone, I'm Bowen. Today I'm here to present our work on phi, leveraging pattern-based hierarchical sparsity for high-efficiency Spiki neural networks. So the presentation will include 4 parts, and I will start by introducing the Spiki neural networks as Spiki neural networks are biologically inspired neural networks that use single-bit spikes to process the information. It has found many applications in several domains, including the robotics, autonomous driving, because its ability to process the temporal information naturally and its low power consumption compared with deep neural networks. So SNNs and DNNs are alike in one point, that both of them spend most of their time on precise the matrix multiplication, but they are different in the activations. For the traditional DNNs, we use activation functions to produce the dense output in the flow point. However, in the Spiki neural networks, we will use the Spiki neurons to convert the multiplication outputs into the single bit spike with zeros and ones. And this will introduce the inherent bit sparsity. This is to say, when we do the computation, we can simply skip the zeros and only compute the ones. So the question is, can we do better than just skip the zeros? And during our observation of the Spiki neural networks activations, we found that they form the distinct clusters. So based on this observation, we define the certain combination of zeros and ones within rows as the patterns. So as you can see in the visualization, there are many activation rows that are same or similar to certain patterns. This is a very strong regularity which we don't find in the normal distribution or the DNN's activations. So the question is, can we use these patterns to save the computations in the SNNs? So based on this observation, we proposed our pattern-based hierarchical sparsity, or the phi sparsity. We decompose the key idea is to utilize the predefined patterns to skip operations. We decompose the computation into 2 levels of sparsity. The level 1 is the vector sparsity that mainly composed of the predefined patterns. And the level 2 is the element sparsity that handles the remaining computations. So here is how it works. For example, we have the online spike activation on the left and 2 selected patterns on the right. And first, we match each activation rows with the relevant patterns. So for the row 0, it is exactly same as the second patterns. So we send the second pattern to the level 1 vector sparsity matrix. And here is how we save the computations. So for the so we can predefine the patterns and pre-compute their multiplication with the weight matrix offline before the inference. And the outputs are stored in the memory. So during the online inference, we only need to get these output results from the memory. So for the row 0, it costs no online computations. So for the row 1, it is also similar to the second patterns. So we will send the second pattern to the level 1 matrix. And here is how we reuse the patterns. That we pre-compute the results of the pattern with the weights 1 time before the inference, but we can reuse them several times during the inference. And the difference between the rows and patterns creates our level 2 sparsity matrix. So for where the patterns has the 1, but the activation rows has zeros, we will put a -1 in the level 2 matrix. And this is our correction term. Level 2 handles these correction terms and compute them online to get the correction output. And for the row 2, it is similar to the first patterns. So we send it to the level 1 matrix. And where the activation rows has 1, but the pattern has 0, we will put 1 in the level 2 matrix. And this bidirectional correction makes us can match any rows with any patterns. So for the last row, because it doesn't similar to any patterns, so we directly send it to the level 2 sparsity matrix. And finally, we add the level 1 and level 2 output together, and we can get the original result as the traditional computations. So for the phi sparsity, the computation we need is only the level 2 matrix. It has 3 non-zero elements, which means that we need 3 computations online. So it is far more less than the original bit sparsity, which require 9 times computations online. So although this phi sparsity can save the computations, when we implement it, we face several challenges. So from the algorithm side, the main challenge is that how to select the patterns. So first, because the activations are dynamically generated online, so but we need to define the patterns offline. And the second challenge is the complexity of the patterns. For example, if we select the pattern lines of 16, we will need more. We will have more than 65,000 patterns that is possible to select. So it's hard to select the optimal subset. So to solve this challenge, we proposed a pattern sparsity calibration set. The observation is that there is similarity between training and test set. So we can use the calibration set from the training data to identify patterns that will also work well on the test set. So based on this calibration set, we propose a k-means-based clustering algorithm to identify the patterns. We first filter out all 0 and 1 hot rows because they don't benefit from using the patterns. Then we convert each rows into a node, and we apply k-means clustering using the Hamming distance. This algorithm will naturally identify the most representative patterns in the activation space. So the k-means centers will become our patterns after round to zeros and ones. So after solve the algorithm challenge, we also meet some challenges from the hardware side. So the main challenge is the memory overhead. So for example, if we choose 128 patterns with a length of 16, we will need 9 times more memory access to read the pre-compute results from the memory. So this will increase the total energy consumption and delay the throughput. So, and the second challenge is brought by the sparsity processing. So, for example, when the different operations need to access the same bank in the memory, we will face the data conflicts. This will lead to the low hardware utilization. So, to solve these challenges, we propose our phi architecture. It composes 3 main components: the processors that generates the phi sparsity, and the level 1 processor that processes the structured per-defined vectors, and the level 2 processors that process the unstructured element sparsity. So the level 1 and level 2 processors work in parallel, and their outputs are combined to get the final results. So for the processor, it includes 3 key components. The first is the pattern matcher. It dynamically matches each activation rows with the patterns. So for each input rows, it compares with all patterns and calculates the difference and counts the non-zero. The patterns that minimize the difference will be selected. The pattern matcher will generate both level 2 sparse map for the level 2 precise and the pattern ID for the level 1 precise. So, and the second, so the level 2 sparse map that generated will be sent to the compressor and packer. So because it is extremely high sparsities, we use CSR-like format to compress the level 2 sparse maps. This will reduce the memory access. And then the compressed data is sent to the packer. Each packer contains a conflict detector that include different multiple windows. And the windows will check the memory conflicts and the capacity of the following adder tree. So the packer then pack the multiple rows into a fixed sized pack and send it to the level 2 pack buffer for the level 2 processing. And then we move to the computation unit. So for the structure level 1 sparsity, all we need to do is accumulate the patterns results. So we design a prefetcher that only reads the necessary pattern weight products. This will also save the memory traffic from the weight size. And for the structure sparsity, we simply use 8 channels adder tree to accumulate the result. So for the unstructured sparsity, we design a reconfigurable adder tree. Unlike the traditional adder trees that will suffer from the low utilization when process the unstructured data sparsities, our design can dynamically reconfigure the connection based on the packs that input and process them efficiently. So as shown in the example, when the input contains different numbers of rows, and the trees will reconfigure to handle both of them efficiently. And finally, let's look at our evaluation results. We first explore several design parameters. So first is our pattern length. We find that when pattern length is 16, it can balance the density between the element density and the vector density. Because the level 1 processor and level 2 processor will work in parallel, the balanced density means balanced workload. And also the 16 of the pattern length will minimize the total density. So the lower density will mean the fewer computations. And then we also explore the number of patterns. So this will optimize the trade-off between the computation cycles and the memory access. The too few patterns will increase the computation cycles, while too many will increase the memory's overhead. And then we compare our architecture with several baselines on both spiking salience and transformer-based spiking neural networks. So first is our efforts to reduce the memory traffic. Our compressed data structure will solve the activation traffic from to about 50%. And our pattern prefetcher will reduce the originally 9 times overhead to the 3 times. And this is our speed up and energy results compared with previous accelerators. We can achieve about 3.5 speed up and 5 times energy efficiency compared to the Stella, the state-of-art SN accelerator that use bit sparsity. And so in conclusion, we propose the phi sparsity. It is a novel hierarchical sparsity framework for SNs that use patterns to save the computations. Our proposed algorithm solves the challenge through k-means pattern detections and can find the patterns efficiently. Our proposed architecture can process both structured and unstructured sparsity. And that's all. Thank you. And I'm happy to answer any questions.